welcome everybody to our energy storage and decarbonization panel. As we continue to walk through this chapter, we're trying to answer a question that we began with. What technological innovations are we exploring to reduce carbon emissions? So today, I'm delighted to introduce you all to four leaders, four experts, each working on different slices of this global challenge. So let's start by going around and meeting our panel. So first, we have Dr. Cao Tang Din, Assistant Professor of Chemical Engineering at Queen's University. So I'd like to start with you, Professor Din. Can you tell us a little bit about your work in your research lab? Oh, sorry, I can't hear you, Professor Din. All right, we can, you can try changing your mic, and in the time being, I'll move on to Dr. Marcy Black. Great, so Dr. Marcy Black is the CEO and founder of Advanced Silicon Group. Dr. Black, how is your work at Advanced Silicon Group tackling the climate change problem?
Well, my first company was Bandgap Engineering, and that company was really focused on lowering the cost of photovoltaic or solar cell. So we used nanotechnology to increase the efficiency of solar cells and lower the cost. And the idea is that if you can bring down the cost of solar electricity, more people would be able to afford to use solar, and therefore they would use less carbon-producing sources of electricity. So that was the goal in trying to lower the cost of photovoltaics.
I see.
Yeah, my current work is actually on biosensing more, but that's because the nanotextured solar cells have already been commercialized and they're being used all over the world right now.
Great, thank you so much. All right, Cal, would you like to?
Yeah, I hope it works now.
Great,
yes.
Yeah.
All right, sure. So the research we are working on has been perfectly described by Professor Tessagen. So actually we are trying to convert the carbon dioxide and water into fuels and chemicals using the renewable energy. So the goal of the project, we hope one day we can make all types of chemicals and fuel that we are using right now from the renewable resources. So instead of digging them from the ground, we are trying to make them from the air, from the clean energy. So one of the challenges in these technologies, as mentioned by Professor Tessagen, is the energy efficiency where we are working on and trying to improve the efficiency. In my group, we also try to widen the product spectrum. So far, when we convert the carbon dioxide into fuel and chemicals, we are limited by a certain amount types of chemical we can produce, so we are trying to widen that spectrum.
Great, thank you. All right, let's move on to Professor William Chu from Stanford University. Professor Chu is also a faculty science at SLAC National Accelerator Laboratory. Will, can you introduce us to your work?
Hi, good morning, everyone. I'm Will, and I'm delighted to be here. So as described by Ted, Cal, and others, I'm working in the field of electrochemistry and energy conversion and storage. The main motivation for my group is really to tackle the enormous challenge of decarbonization. And there are two particular areas we're working on. One, it's to electrify transportation, something that has already been happening on a massive scale, much work still. And we're also very interested in increasing renewable electricity for the electricity grid. So we're developing a wide range of chemistry to enable these two goals. My research is really at the intersection of fundamental science and technology. For example, looking at both the molecular nature of electrochemical reactions, but also look at their applications, for example, in batteries, CO2 electrolyzers, and so forth.
Thank you, Will. And last but not least, we have Dr. Heather Trajano, Associate Professor in the Department of Chemical and Biological Engineering at the University of British Columbia. Dr. Trajano, what questions are you investigating in your lab?
So I'm a bit of an oddball compared to the rest of the panel. So in addition to being part of the Chemical and Biological Engineering Department, I'm a theme lead for the Bioproducts Institute, and my research group looks at how to deconstruct biomass and then reconstruct it, process it to make new materials, new chemicals, and new fuels. So my career, or my PhD, I was interested in lignocellulosic ethanol, so converting poplar into ethanol. And now, since joining UBC, my focus has shifted much more to taking advantage of the uniqueness of BC species to make advanced materials and chemicals. So we take advantage of the chemical complexity and the complex structures that exist within biomass to create unique materials that will displace fossil fuel, petroleum-derived chemicals and materials.
Perfect, thank you. So thank you all for your introductions. So there are some common themes that I would like to revisit. Our conference aims to discuss technology at the nano level. And one thing that seems to get brought up quite frequently is catalysis. So Professor Ted Sargent explained catalysis. Cal, clearly you work a lot with catalysts as well. And I know, Heather, in your work, you deal with chemo catalysis. So some reports quote the global catalyst market to be worth up to $30 billion, and that was in 2020, so quite a dated figure. So I think we'll start with Cal. Can you explain what catalysis is and its role specifically in your technology?
Absolutely. So we heard a lot about like how the catalysis help us. So what is the catalyst? So this is basically it's a substance, a material that you add into a chemical reaction in order to change the way that the reaction proceeds. So normally you want to increase the reaction rate, or you can also use the catalyst to reduce the amount of the energy you need to put into the reaction, so you can increase the energy efficiency. But I guess the one of the most important role of the catalyst is like you can change the way the reaction occurs, so you can produce the desired product, even though you start with the same starting material, but you can make different type of products using the different catalysts. So that is how the catalyst help, and the catalyst is one of the most important component in chemical industry. So without the catalyst, we would not have all of the types of the chemicals and fuels that we are having now. So imagine that like all of those material comes from that viscous black crude oil. So we start with the same black crude oil material, but thanks to the different catalytic process, we can produce different types of products. So that is how the catalyst is important to our life.
Perfect, thank you. And so I'd like to pass that on to Dr. Trajano. So Dr. Cao explained catalysts in the context of his work. And like I mentioned before, you work with chemo catalysis in your lab. So in what ways is the catalysis that Cao discussed similar and different to the technology explored in your lab, other than the exact applications?
So I would say there's two components to my lab. So there's what's on the webpage, which is the chemo catalysis side, in which case it's very similar to what Cao just described in terms of using typically a metal phase on a support to tune the selectivity of the reaction, to adjust the relative rates of different reactions. And so one of my recent projects was using catalysts to adjust bio-oil into hydrocarbons that look more like our standard alkanes or standard gasoline molecules. And so in that case, the catalyst is playing the same role. The other area that we use catalysts in my lab is we use biological catalysts as well. We use enzymes for when modifying cellulose substrates. And so a recent example from my lab of enzymatic hydrolysis is we've used different cellulases, which are enzymes, proteins, that target specific portions of the cellulose molecule. So cellulose is the sugar polymer, cellulase is the protein that attacks it, and by tuning the type of enzyme that we introduce, we develop different fiber properties in the cellulose. And this is important because the fiber properties, or the properties of those cellulose fibers, is what controls our final paper products and the features of those. So the example I always love to give when talking about paper is, so this is paper, but so is, one moment, this, and so is cardboard, right? Your Amazon box. These are all paper products from a paper maker's point of view, but the fiber, the way we develop those properties, obviously very, very different. And so we use enzymes to tune properties so that we can create more advanced materials.
Great. And just maybe a small follow-up, are you specifically designing the enzymes, or are you sort of filtering out specific proteins from like a large batch of enzymes?
Right. So design of enzymes is obviously a very active research area, but that's not my expertise. I collaborate with the enzyme designers and work on the application and scale up opportunities where it makes sense.
Great, thank you.
Yeah.
So now I want to switch gears a little bit, and I want to turn this to you, Will. Can you explain a little bit more about what got you looking into specifically how reactions occur? So we have many students in the audience, and right now our idea of redox reactions is basically just a transfer of electrons. You have the oxidation reaction and you have the reduction reaction, but beyond that, it's sort of a mystery. So can you explain what it means to study these reactions using a bottom-up approach?
Sure, Ethan. So this is a great question. The answer is quite extensive, so I'll try to be brief. I think the very fun part of redox chemistry is that it's very length time spanning, which means that, for example, in terms of length, you can think about redox reactions starting from the nth level, so at the molecular level, all the way to the system level, right? For example, looking at a reactor or a battery system for a car. So it necessarily involves about, say, 10 to 12 orders of magnitude in length scale. So at every single length scale, there's something interesting. So as I mentioned, you have the quantum mechanical length scale. This is where the electron transfer happens. You have the particle level. So this is looking at the mesoscale, the nanostructure. If you're talking about electrolysis, then you can think about electrodes. So this is maybe tens of microns level, and so on and so forth. And similarly, you can also think about the time scale, right? So if you think about the molecular reactions, the very fastest step goes on the picosecond level. The rate limiting step may be at microsecond level. And then if you look at the lifetime of the catalyst or the electric catalyst, there's many years, sometimes 10 or plus years. So I think to study catalyst means to understand and control all of the length scales and all of the time scales. And it really requires understanding of the science, also engineering and control of the systems. So that's usually how I think about the playground for someone working on catalysis, is really to think about the length spanning and the time spanning characteristics of
Great. Yeah, I think that was a perfect distillation of, like you said, such an extensive topic. But I think it really does put into perspective the importance of starting small and truly understanding the fundamental science behind it, and then working up from there. Great. So next, I'd like to zoom out a little bit. Marcy, we learned, you mentioned a little bit about the nano-textured solar cells that you developed at Bandgap Energy, and how your team engineered the material such that the increased surface area was actually a benefit rather than a drawback. So by engineering this material, you were able to increase the overall efficiency and eventually commercialize it wide scale. So on that point, one of the biggest hurdles in research and development is bringing technology from the lab bench to the market. at scale. So what steps have, or what lessons have you learned at Bandgap Energy and at Advanced Silicon Group taken to overcome these challenges of commercialization?
That's a good question. So first I wanted to say that we also use a catalytic reaction, but I'm not really studying the science of it. We're really applying it to making a product. So the way that we make our nanotexture, our nanowires, is we deposit a thin layer of metal, and then we put it into a HF in an oxidizing solution, and the metal catalyzes the etching. So it etches where the metal's touching the silicon and not where it isn't. And this ties into your question, Ethan. When we were starting to look at commercializing for solar, you need football fields. Sorry, I'm from America. So we need football fields of nanowires or nanotexture. And so we know we needed a low-cost, scalable process. And this process of doing metal-enhanced etching was known to be very fast, very cheap. And I looked at it and could tell it would be scalable. The problem was it wasn't very controllable. So instead of taking a more expensive technique and trying to make it less expensive, we went the other way and took a technique that we knew could be scalable and low cost and tried to make it more controllable. So I think when you're trying to commercialize technology, even from the very start, you need to keep the market in mind and the market needs and try to design for something that could eventually fit that market need, whether it be cost or performance.
Right. Yeah. Thank you for your insights. Great. So thinking more broadly about each of your career paths, I'd like you to think of and offer one piece of advice that you have for current students who are currently in the process of figuring out their own careers. So let's start with you, Heather.
Just one piece of advice. That's the tough part. So I guess I'll keep it to like two closely related pieces of advice. The first is that I got was that when you start getting comfortable, you need to find something that scares you to push yourself to the next opportunity. And sometimes that just means so the reason that I went to the grad school that I went to was that I was at a conference about biofuels and there were some professors speaking there, and it felt really intimidating to walk up to them and introduce myself and say, I'm looking for grad schools. But that's what I did. And one professor was kind of a jerk about it. But the other one was really, really lovely and very helpful. And I ended up joining his group, and it was a huge springboard. But that also mirrors the other part of it, which is to seek out mentors and let them know where you want to go, what you're trying to accomplish next, and they'll help you. They'll give you advice on how to prepare for that, how to introduce you to the next point, open some doors, and that's those two pieces of advice combined: people and the people around you, and pushing yourself out of your comfort zone.
Thank you, Heather. And I think this definitely applies to this conference broadly. Now, all of you on the panel, you're the professors and the people that our young students are looking up to. So this is just a message to all the students watching. Go outside your comfort zone, start that chat, send that email. And yeah, I think this is definitely a great lesson for me included as well. So thank you. All right, next let's go to Cal. What is one piece of advice that you'd like to offer?
Well, I would suggest to explore different things. So one thing we learn is that we sometimes we do not know exactly what we'd like to do when we're actually working on those kind of stuff. So it's trying to explore various different things before you decided to your path of your career.
Perfect. Short and sweet, but especially relevant. Thank you very much, Cal. All right, let's go to Marcy. what piece of advice do you have?
Well, I definitely agree with the mentor thing, but I'll add a new one. I think it's important to combine what you're passionate about with what you can make an impact in. And so for me, I was always interested in electronic materials and optics, but I recognized that energy and environment was the biggest problem of our time. So I was able to combine those two, as well as healthcare, which is why now I'm looking at biosensing. So I think it's important to be realistic of what your motivations are and what you enjoy, and try to combine that with making an impact in the world.
Great, thank you. And so, yeah, I hope some of you watching, we're exploring the different facets of nanotechnology, so perhaps you might discover something new that you didn't know before, and perhaps that might end up being your passion. So again, especially relevant, thank you. And finally, let's go to Will. What piece of advice do you have for our students?
Well, so many great things have been said. I'm not sure why I can add, but I guess I'd say two things. Maybe the first one's a little provocative. I'm always very wary of making long-term plans. You know, what are you going to be 5 or 10 or 20 years from now? It's almost impossible to know. 20 years ago, I had no idea what I'm going to be doing today. So I think, you know, pursuing one's career is really about making choices, you know, maybe 1 or 2 or 3 years into the future, and you make one choice at a time, and you make another and another. So I think it's important not to overly restrict yourself and say, I really want to work on, you know, nanotechnology and medicine. That may be too restrictive, and then you're not allowing yourself to open up special doors that may come your way halfway through your journey. So I think this has worked really well for me. I actually never wanted to be a professor, but I just sort of made one decision one after another, and then that led to where I am today. So I think giving oneself the freedom to navigate a sample, I think it's a really awesome feeling to have. The second thing advice I want to offer is recognizing that the way we approach science engineering really has changed. You know, I started doing research 20 years ago, and at that time, it's really about doing things by yourself. It's about earning your degree. But now I think it's a much more team-based approach. And the reason is very simple. We are trying to solve very large problems, and often there is a clock that is ticking. So I think the more you can embrace a team-based approach, thinking about the reward not only to yourself, but also to the team and, you know, to the community at large, can really change your perspective. In my own research as a professor now, I really, for example, value collaborating with industry. I really want to learn what they are thinking. And it's not just about my group doing its own research in its small little confined circle, but really working collaboratively with others. And sometimes that means you have to give up certain things. You may not be able to make all the decisions. You might not get all the credit. But I think science and engineering as a whole really gets advanced when you take a team-based approach. So those are the two advice I have.
Great. That was perfect. Thank you so much. Yeah, so there are some very, very great takeaways from all of your answers here. And I'm sure that everybody listening, and myself included, we will be using those lessons and implementing them definitely through our career paths moving ahead. So we're at 11:43, and I'm not sure if we have enough time for questions from the audience. However, we do encourage everybody to reach out to some of our panelists if they will be sticking around for the rest of the day. I know you guys are busy, but email also works as well. So if you have any specific questions you have to follow up with our panelists today, then we encourage you to do that. So just to wrap up everything in, I guess, a nice, neat little bow, we started this panel discussion by considering a question. How do we reduce the carbon emissions that are the driving factor behind climate change? And so Bill Gates talks about the 75% problem. When we think of renewables and decarbonization, I guess our immediate thoughts are looking towards solar generation or renewable power generation for electricity. But electricity only contributes to 25% of total carbon emissions. The rest comes from agriculture, manufacturing, the extraction of fossil fuels from the earth. And those form this large amount, 75% of the carbon emissions. And so today we learned about some of the new technologies that are both tackling the electricity generation and storage, but also looking towards things that might upend current standards in manufacturing. So new ways to develop fuels for transportation or for other activities and operations in industry. So I think it's really important to understand the holistic view, take a step back and look at the entire industry as a whole, and realize that there are many facets to the decarbonization problem. So I think that wraps up our discussion panel on decarbonization. And I would like to thank Marcy, William, Heather, and Kao for joining us today. I think it was definitely a very, very, very insightful conversation, and that everybody watching found a lot of value in this as well.
Thanks for having me.
Yeah, thank you for having me too. Yeah.
Thank you, Ethan.
Yeah.
Thank
you for the invitation.
Great. All right, so this brings us to the next segment in our environment chapter. The last part of the environment chapter is our breakout sessions. So in the sessions page, there will be two choices for you. We have two amazing speakers working in different areas of nanotechnology and the environment. First, we have Dr. Soren Brandt, who will be talking about his research at Harvard on developing a liquid sensor for detecting environmental hazards. Our second breakout speaker is Evelyn Allen, who will be discussing her work as the CEO and founder of Evercloak, a clean tech materials company. So that is the end of the main stage segment. I'd like you to make a choice between those two breakout sessions, but there is no wrong choice. You will be sure to learn lots, no matter what session you choose to go. So I'll leave that for now, and I guess I will see you at the beginning of our next chapter, information. Thank you all for coming.